So thank you for the introduction and thank you for the invitation. I'm very happy to be here and to have the opportunity to talk about, I mean, I will talk more about the studium than about my science, a little bit in the spirit of Vince, hopefully with a little bit of his talent about that, because there's a lot of connection between my arrival in France and the studium, because I am a coordination chemist and a spectroscopist of Lanthanide. I was previously, I'm Swiss actually, I'm Swiss. I stayed for a long time in US. I did my tenure at University of Pittsburgh, and it's through the studium that I was able to arrive at CBM, and that's something which is very important because it really had a strong impact on my science at many steps. And that's what I want to show today with this presentation, which will contain some science, but that's basically will be a mixed between science and other consideration. So first point, the CBM, which is a very important place because that's a building that Paul Vigny was directing for many, many years. And if we have now this beautiful building and this renewed building, it's thanks to him. So he was able to basically create the momentum to have this lab, and it's so far the best lab I ever had. I mean, I moved few times in my scientific career. And I'm sorry for the picture because I didn't realize that I don't have a high resolution picture. And actually, the building, the last part that was not renewed just got renewed. So it's all very, very nice. So, and the Centre de Biophysique Molecular is a very special place because it's a unique place where you have chemists, it's dependent on chemistry, biologists and physicists on the same location. And that's really, you don't find that many places. When I was in Pittsburgh, I had a major appointment in the chemistry department. I had an appointment in the medical school a little bit, and also at Carnegie Mellon, where we have the imaging system. So we have kind of the similar type of access to facilities, but not at the same place. So what happened is that I was contacted actually through Jean-Claude Belleuil, who spoke with Paul Vigny, who spoke with Eva Toth about, because they were looking for someone who can take over the group of Jean-Claude Morizot, who was going to retire, and they were looking for a successor. And they, Eva came to me and said, maybe you should come and visit CBM and see if it's something that will be attractive for you. And we have this unique mechanism that allows you to stay for 1 year or more, actually, to get acquainted with the place and also to be acquainted with the people. And that's happened like that. So basically I move and I successfully actually managed to get a permanent position first with University of Orléans and then with the INSERM. So that's really was a success story, but that's not the only things, because as you will see through the different steps, Studium came to help us and to really give a lot of momentum to my group at many steps. So I want to talk a little bit about science in the beginning. I want to talk about biological problem. I don't want to go too much in detail about that because there were many presentations, beautiful presentations, where we had a situation where you need to identify a very small object or a very small concentration in a complex environment. So that's a haystack. So typically, biologists, medical doctors, sometimes they have this problem. And it's very often almost impossible to find because you don't see where the needle is in the haystack. So one approach that you have to override this problem is to start to work with light, with optical imaging and in the near-infrared, because you can uniquely make the haystack become smaller. And very often, what you need to detect, early stage tumors, metabolites, that's exactly the situation that you have. And you cannot purify the sample. You cannot, because it's just too small or too difficult to manipulate. So, and the haystack is actually autofluorescence. So biological tissue, when you want to work with them, one of the difficulties that you will have is that they themselves have their own ability to emit light. They will, when you excite with light, they will emit light. And one way to be able to get rid of this unwanted autofluorescence is to shift towards the near-infrared. And that's really what I had since I started my independent career in 2002 at University of Pittsburgh. That's what I had in mind. To take advantage of this unique strategy, but for that you need to make compound and you need also to go to biological application because it's very nice to have a nice object, chemistry object, emitting in the infrared, but you need to be able to use it and to demonstrate that it's really work in the real world. So this is really the problem that we have in mind, is this quantification, this identification of small of analytes, either like with small size or in small concentration, and with this common point about having sample in a complex environment, in a matrix, in blood, in tissue, in organs. So that's the common point. So for that, you need sensitive detection to be able to detect typically like the small object. You want this detection to be non-ambiguous. You want to be able to have a clear statement about it's present or it's not present. If you think, for example, I think Vince cited this example like this morning about situation where you have like surgery. The surgeons, they want to know if there is a tumor or if there is no tumor. And there is no kind of route for like mistakes. And you want also to be able to do that in real time. On fluorescence, emission of light is good for that. That's one of the few imaging techniques when you can obtain this advantage. In addition, with the advantage of having small instrumentation. That's another point where you need to think about light compared to MRI, compared to PET scanning. This is very small, and this is what we have in our lab. This is a research equipment, but when we want to make a device, actually, we can just take a lens and a camera, and that's it. And you can do like a lot of imaging with that. So technology is there, and technology can be moved to the patient, can be moved to the experiment. That's something to keep in mind. Near-infrared, it's really a domain now where there is a lot of demand from biological research and from surgery. And there is additionally the near-infrared 2 domain compared to the near-infrared 1. I don't want to go too much in detail, but right now, so these are wavelengths, and you're very familiar with the visible because that's what we see. We see more or less until like 650. The CCD of your phone see a little bit like further. But you can go up to like 1800 nanometers, and this is the domain where you start to have like different properties of light, and we're not aware of that. But at this region, you have a very low absorbance of biological system. Vince made the demonstration this morning with his finger. You can go deeper. The further, like the higher the wavelength, the further you go. Another advantage that you have is the fact that you have less and less autofluorescence with the wavelengths. And last but not least, you have a lower scattering. The photons that will go out of your biological system will be less scattered. And the consequence of that is that you have a much sharper image compared to the visible, compared to the near-infrared 1 domain. So a lot of demand for that, including for the surgeons who want to take advantage of this sharper image. I will take a little bit of water because so for that we use lanthanide. So one of like the specialty of the group is to take advantage of these metal ions, and you know the most famous one is perhaps the gadolinium because it's used for MRI contrast agent. There is a lot of chemistry with that. This compound can be proven to be stable, to be usable, and to be injectable. But the other lanthanide that you have in the series, they all have like similar type of chemistry, but and in addition, several of them have the ability to emit either like visible or near-infrared light or both of them. So you have a lot of choice on what is more impressive is to see like the different like signal that you have with these different lanthanide metal ions. Each lanthanide metal ion has its own like color, and as you see compared like to each other and compared to organic molecule, you have an overlay here between a lanthanide, an organic molecule, which is in the green, and in blue you have like you have a quantum dots. So you see it's much more sharper. It doesn't shift. They always are appearing at the same position, which is very convenient when you want to do a filter for your microscope. And you can do multiplex because they don't overlap much or at all with each other. So a lot of possibilities with that, not that much exploitation. And last but not least, you have a lot of several of these lanthanide metal ion will emit in the near-infrared 1 and 2 domain. So this is a challenge that we have in mind to benefit of this system for practical application. Vince showed an example this morning. So another advantage of this compound also compared to organic fluorophores is that they don't photobleach. So they will not decompose when you expose them to light for an extended period of time, which is very convenient just to work on the bench with them, but also like to prevent the risk of a false negative because the compound has been decomposed. So these are the advantage of the lanthanide. The downside is that like, if you go and buy your favorite lanthanide, you will be very disappointed because you will see nothing. So these are cuvettes on top of a UV light. They fill with water containing opium nitrate, and you see nothing because all this transition that you have seen is forbidden by the Laporte rule. And the way to override that is to put in close proximity another molecule that will remove this forbiddenness by absorbing the light from the excitation, converting the energy to the lanthanide metal ions. And that's one of the key aspects of our work, is to design this antenna, this molecule that will absorb the light and transfer, and make them work in the real world and make them work with the infrared. I will not go into the detail of like the mechanism. There is a lot of spectroscopy behind that. There is a lot of energy transfer. There is a lot of arrows. So there is a lot of mechanics to understand. And that's part of the work we're also doing at CBM to rationalize the properties of this compound to be able like, to design them better. And that works very well, for example, for the metallic crown. Vince has described some of them this morning because we have been able like, to go to very high quantum yield, for example. So the beginning of all that at CBM, that was my arrival at CBM, so that was in 2008, so I stayed back long, actually, because that's, at that time it was possible to stay back longer. That was long enough, actually, to be able like, to secure this position at university and to take over the group. So I was installed, and basically, from the beginning, having, and you may recognize this lady, some of you, this lady, Alexandra Foucault, who was the first grad student that I had like in Orléans. She's a biologist. She's not a chemist. She's a biologist who had the courage to go with a chemist and got excited by the challenge. She knew the interest of like solving this problem. And she joined my group. And then I realized that, I mean, she was able like in a very short amount of time to solve not really a problem that we had, but we developed like this system. Here you see a metal organic framework. It's a rigid coordination polymer with a big cavity. We designed that with my colleague at University of Pittsburgh, Nathaniel Rossi, because you can have a large amount of lanthanide metal ions and a large amount of antenna per unit volume. It's a way to have more signal because we didn't know how good the quantum yield would be. So that was the strategy. We designed this object, which was initially large, and through the work of Alexandra, she was able like, to make it small, to miniaturize it, and to go to the point that we could do the first demonstration ever that it's possible to use this compound to emit ytterbium light in living cells. And that was really a little revolution because you can read in papers at that time that it's just impossible. People were claiming that there is no way, there is not enough signal. My PhD advisor was stated that in a paper. And so that's really opened a new perspective. And one of the reasons is because she had a very different way of thinking about how to use this compound in a cell. So she didn't go, and she kind of told, actually, Nathaniel Rossi and me, not to go for the complex solution that we have in mind, but to go straight to the cells. And that worked. So that was the first kind of like discovery for me of the advantage of being in a place like the CBM through the studium. But we need also spectroscopists. So at one point, like the group at that point got like one permanent ingénieur de recherche on Alexandra, that was it. So basically at that point, like for the spectroscopy, I was in contact with Vedana Eliseva, who did actually a postdoc in the same place I was a PhD. So we had a very strong background in spectroscopy, and And I managed actually like to convince her to join the CBM thanks to the studium. It's a conversation we have with Paul Vigny about that, because she had an outstanding dossier. She was a fantastic candidate with gigantic dossier of publication. But it was difficult to attract her in France because the salary compared to England at that time, you know, and the studium made the difference. Convince her that this could be the difference, and that works very well because she basically like started to work. I will show you a little bit of the research she did at that time. She was studium in the beginning. During the studium time, she got a Marie Curie, and that's allowed her actually in the end to secure a CNRS chargé de recherche position, which she got like in 2015. So the story was very successful, and that was the second studium fellow who got stabilized through this, actually the third, because Gunther in the room was in between, I think. And just like to show like some examples, so Svetlana at that time was working with other like polymetallic system where you have a large number of metal ions to emit light, and the antennas are outside. It's organic in that case. It's kind of a flexible molecule. And I will not go too much in detail, but Svetlana like developed like a samarium dendrimers that has this unique ability to emit near-infrared and visible light, because the metal ions do both. And that's allow us to make a very nice paper in Angewandte chemistry. Sorry, like I'm going too fast here. In Angewandte chemistry, because we have been able, thanks again to the ability to do the biology, to test this compound like in a cell, in a living cell. And that's something chemists cannot do. So that was really also like something that we needed the CBM, and we needed to have like a biologist experience to be able know how to be able like to do that. And Alexandra also like was the person who did that, was very persistent because this compound was not very soluble. So they managed to figure that out. Got, and we don't see it because the projector is not fantastic, but they got the near-infrared like signal from this dendrimer in cell. That was the second paper describing near-infrared emission from a lanthanide compound in a living cell. So, and that's, we were able to publish that in Angewandte Chemie. So that was really exciting because we have two systems at that time. And we have been with this approach to do the first test on small animal, because that was one of the goals, is to see if we can have the light going through the tissue, if we can detect these dendrimers through the skin of this mouse, and that's what we can see here. We just got the first piece of equipment, so that's also like make a proof of principle that it's possible like to go like in vivo with this system, even if it's not the case of this mouse, which was that we sacrificed for this experiment. So that's what we, I mean, we did, of course, many more since then, but another point that was also like very important for us is the Studium conference, because that's something that didn't exist at my time, but when Svetlana arrived, it was possible, and that was a unique opportunity to organize a conference on luminescent lanthanide, and we have been able to invite a very large number of people. We made a pretty big conferences, and that was a way to highlight that we are here, that Orléans is an important place for lanthanide coordination chemistry and for lanthanide biological-based imaging. Lausanne was the place before. Eva Todd came from here, I came from here, Svetlana came from here. So basically, like, that was a way to show that, no, there is a new place where all these skills and all this ability appears. And this conference was really something that people still talk about it and never understood that it was for a fellow. It was not like something that will happen every 2 years or 3 years. But if it's possible, they will be happy about that. But that's really create a lot of attention. And then, with the idea to get like more expertise through the same mechanism of fellow, we were able like to have Guillaume Collet that unfortunately not be with us this afternoon. He was here this morning. You may have seen him. So Guillaume is a brilliant like biologist who has a lot of training in cancer, but in cancer like biology and cancer growth of tumors and cancer model. but he also like acquired through postdocs experience in formulation and also like in chemistry. So he became like very multidisciplinary, and we through the studium we were able like to make him come back to Orléans, come back to CBM. He did his training at CBM with Claudine Kieda, but really as a biologist he came back as a multidisciplinary researcher. That was in 2019, and actually he developed like a project which was very interesting because he developed also metal organic framework. You have seen a first model of this rigid organization, except he wanted to have something that can deliver like molecules, that can deliver drugs. So he used a pretty original approach when you assemble like molecule with light. You assemble with light, you disassemble with light. So, and it's allowed to make what he call responsive morph, that you can control actually like the release with light. And this is what you have here. You have like a demonstration, and it's pretty spectacular. There is a movie actually. So that's the morph when it's complete. And he used actually his ability to do like imaging of like large objects. As you can see, he makes these different morph melt, disappear. You can see really kind of the disappearance of the morph. It's much better on the screen, but the paper just got accepted, so it will be like minor revision. So it should be out soon, and you can see the movie where you really see the disappearance of this system. It's very controlled. It was fully controlled. On this morph, another interest that they have is because of the cavity, you can put drug inside, but you can also put antenna, which he did. He put fluorescence. That's what you see here. And when you have like fluorescence inside of like the morph, you can use the fluorescence to do confocal microscopy on the crystal. So you can see the crystal, and that's how he was able like to monitor this modification. It changed over time. And you can also sensitize the lanthanide, so you have the antenna inside. So you have, in addition, a way to deliver like molecule, but also to track the location of what you want to release. So Vince talked about that because we had like other action. On one of these action, that was a consortium. And Vince, I think, said like really all of it. But that's also like was very good to keep the momentum, create a dynamics, having all these different like colleagues coming like to visit us on a regular basis. As was shown, that started like many projects, including this nanothermometry, but also other one. And it's also like through this that we have been thinking about, like, I mean, it was possible to convince Peggy and Vince actually like to commit for this professorship and to have them with us for 4 years with 3 months each year. And this has just been starting this year. And this is very exciting and very productive for us because it's kind of being on the daily basis like as colleagues. So, and it's also like good, I think, for the group because both groups will start common group meeting. It's very like it's a good momentum. So time for me to do some acknowledgement because, as you can see, Studium was really extremely. That was a key advantage on to really make the research transfer well from US to Orléans, but it's more than transfer. It's really blossom because we got all this additional possibility that would have never happened in my previous place. And I would like to thank all the different like people who help us this to happen. Of course, Paul Vigny, who created the Studium and this fantastic institution with a unique spirit. Harry Bruand, Monsieur Gino. Maryse, at that time, like it was Maryse, Michel, Marie-Frédéric already, Yves Duranton were taking care of us. After that, like Yannick, and then like Aurélien and Sophie arrived. So we have been working with many of like Studium members and the younger generation who do a fantastic job like to welcome us like in this great symposium. So thank you really so much for the support. Like we will not be like in the situation we are today without the Studium, and happy anniversary.